So before we go any further, we are an Apache open source project. A lot of the team, we work at Yahoo, but we are top-level project, and all of this that I'll show you is available on GitHub with the source code for you to view. So unsurprisingly, the reason we're all here is because big data, it's big, and it's getting bigger. By 2025, there'll be almost 200 zettabytes in the data sphere. In the same time frame, we're expected to be generating almost 500 exabytes of data daily. So it's big, it's growing, it's coming quickly. By 25, we're expecting almost 100 billion IoT devices. So these a lot of the time are sensors that are collecting a lot of data. And the market is huge as well. 2020, it was about $200 billion, projected to be almost $700 billion by 2030. And in light of all of this, the companies that we each represent here today will be doing data analysis on that ever-growing data set. Or, sorry, on ever-growing data sets. Performing the analysis, it costs time and it costs money. But Sketches will allow you to process the data order of magnitudes faster. And the way we'll do that is by reducing the memory requirements of the algorithms, again by orders of magnitude. What this is going to allow you to do is to perform your data analysis in near real time. And in comparison, brute force analysis just won't be able to do that. Now, the bigger the data is, the more dramatic the benefit you will see if you adopt using sketching algorithms. And of course, time and space is money, so if you really invest in understanding how these sketching algorithms work, it will save you in the long run. Now, I imagine that for a lot of people here, sketches or sketching algorithms is an alien concept. And in my opinion, the alien that we'll choose is Grogu. Have we got any Star Wars fans here? At least one, that's good, at least two. Okay, so for those of you who don't know Grogu, that's absolutely fine. But Grogu is this little green guy. And the first thing you notice about Grogu is that he's tiny. And that's just like sketches. Sketches are really, really small. In fact, we're going to be talking about things that are like kilobyte sized. Grogu, we don't really know how old he is, but he is quite old. And he's almost certainly not grown much. And that's like sketches. Either they stay the same size, or they just don't grow very much. Another thing we like about Grogu is he travels everywhere in a little pod, and he always fits in this pod. Again, that's a bit like sketches. Once you instantiate them, and you get them into memory, they can stay there. They're small enough that they don't grow outside of your memory budget. But moving on to point 2. Grogu's got his companion, this big guy, he's called the Mandalorian, and a lot of the time the Mandalorian gets himself into trouble. Grogu has some special powers where he can look at the Mandalorian and decide whether to help. But he only gets one chance to see the Mandalorian in action. If he doesn't perform there and then there is going to be a problem for both of them. So Grogu operates in a single pass view of the world. That's like sketches. We process data once, and then at the end of that stream, then we make a decision. Similarly to the previous point, it doesn't really matter what trouble the Mandalorian is in. Grogu only really has one way of responding. Again, like sketches, it doesn't really matter how you present the data, whether it comes in some funky order, whether we have late arrivals. It doesn't really matter what the data distribution is. A lot of these algorithms come with worst case guarantees that when you ask it to perform a certain query, it will respond given particular error bounds. And I'll be honest, I'm going to exhaust the metaphor probably a bit too much. Sketches are highly parallelizable, and I didn't know how to squeeze Grogu into this one. But being parallelizable, this is great when we're talking about large-scale distributed systems that are very much the paradigm in which big data analysis is performed. So you might be thinking, this sounds a bit too good to be true. We've got these small objects. We're going to be doing big data analysis. We can view the data once. They operate in parallel or distributed systems. How do we achieve it? And the real point of difference and the the idea that I'd like you to challenge of yourselves is this. Can you sacrifice an exact solution for an approximate solution? I agree. There are business applications when you very well may need 10 to 16, possibly, digits of precision. But for a lot of things that we're interested in when it comes to data analysis, I think that is overkill. And if it's overkill, then we can approximate. And when we accept this view of the world, this is how we can get huge, huge wins. And to illustrate this, I'm going to start with a simple problem. The problem is one of the most fundamental data analysis tasks. It's counting unique identifiers. So you can be counting words, search terms, customers that you see daily, customers that you see over time periods. You can be counting application users. The canonical example is monitoring IP address flows, but this is everywhere when it comes to large-scale data analysis. And I imagine there are a bunch of you in this audience right here, right now, thinking, counting uniques is easy, it's straightforward, I don't need to listen. And I'm hoping to convince you that you're wrong. So let me start with a simple problem. There are going to be a lot of people here today talking to you about streaming solutions. And I think they do offer streaming solutions, but what I would say is it's not the most interesting or compelling of streaming solutions. And this slide exactly gets to the reason why. Let's be clear about what we're talking about. A data stream, it's a very large data set that I can't fit into memory in one go. So I need to read that data stream item by item. That means the data stream has a start point and it has an end point. The items are read in and they arrive through time. But at the end of the stream, I return an answer to a particular query. Now, before getting on to count distincts, the reason why I think this is different to other offerings or other views of the streaming world is that if we just want to monitor, say, time spent on an application or the length of a stream, how many total items are in this, what's the total weight in the stream, that's easy. You just keep a counter, so it's not an interesting streaming problem. This gets to what interesting streaming problems are. I'm sure we're all capable of going through this stream and evaluating how many unique emojis are in the stream. But I reckon for most of us, we're going to get like halfway through and then start having to backtrack and say, OK, have I seen this item before? And answer yes or no. If I have seen it before, I won't increase a count for my unique counts. And if I have not seen it, then I will add one to my tally. And this is pretty much abstracting away a bunch of details. What happens in a query engine? We have a very, very large data stream. And every time an item is read in, the query engine will generate a hash of a particular identifier. If the identifier has not been seen, then it will flip a 0 bit to a 1 bit. But what that means is, casting our mind back to the previous slide, is that if we have n unique identifiers in the data set, then I'm going to need n bits just to generate a data structure that essentially keeps that tally for me. Again, you might not be thinking that's a problem, but let's not go from small problems. Let's really scale up. Again, this is not too huge, but when n is about 8 billion, then I need to store a gigabyte-sized map in memory just to be able to answer that really simple query, which is how many uniques are in the data set. And then once I've got that bitmap, what do I do? Well, I just scan through the bitmap, I count the number of ones that are set, and that's my count. So yes, we can do it, but is this an ideal approach? I think not, and I think this is where sketches come in. So what are sketches? Well, they're cleverly designed small arrays where the clever design is in the algorithm design. Typically, this is some special type of random sampling or particularly exploiting particular hash functions that do some sort of deduplication. Their size is parameterized by something called k, that we call the number of buckets. And this k governs how large the sketch grows in memory, and that's decided ahead of time. We store this object in memory, and then the query processor can operate over the object in memory and return an approximation. The approximation for all of the sketches in our library comes with mathematically proven bounds to give users confidence in the outputs. And unsurprisingly, the size parameter k is directly related to the error or the accuracy of the estimation. What this means is we get our first win, a small query space. So sketches start small, they stay small, they don't go out of memory, irrespective of how large the data is. And we can just view the data in a single pass and return an estimate of our original problem. And again, when I say small, please, I really mean that. We are talking kilobyte-sized objects, even if your data is huge and can't be loaded in. But of course, this is an oversimplification of the world. Typically, we see something like this. And I'm sure many of you are familiar with these types of diagrams. It's like a MapReduce view of the world. But again, let's step back and think what's actually happening when I do this. I've got a large data set, and that large data set is partitioned over various nodes that are called the mappers. But typically, the number of mappers is small-ish relative to the size of the data set. So I've only reduced the amount of data going to each node by something like a constant fraction. If it was huge to begin with, it's still huge at the mapper. Then for the count distinct problem, what happens at the mapper node? Well, each mapper generates a bitmap similar to what I mentioned to you earlier. We can represent it as a dictionary of key-value pairs. So if the data is large going to the mapper, then these summaries, the dictionaries or the bitmaps, they themselves are pretty likely still to be large. What that means is the next phase, which is often the copy or the shuffle phase, is super, super expensive. And once they get to the reduction, all that happens is the reducer joins these tables on the keys and then increments counts. This is a real problem because we haven't actually changed the complexity of the query at hand. All we've done is palmed it off to more computers. So I don't really think this is making our lives any easier. And this is how we can exploit sketches. All of our sketches in the library benefit from something that we call a merge operation. A merge operation is great because, as you can see down here in the blue and the red, I can generate two sketches from two independent data sources. Again, these sketches are small. I roll the two sketches into something that I call a merge sketch. The merge sketch has the same size as those two sketches in red and blue. Another benefit of the merge sketch is that it has the same error properties as had I viewed the two independent data sources one after the other. So what I'm doing now is processing my data once, making one sketch, then I can ignore the rest of that data set, and that sketch is small enough to hold in memory. Then for the second data set, read that data set, store the sketch in memory, and then ignore the data sets. Merge them again still in memory, and I've got my merge sketch having processed the data sets only once each. Now when we go back to the MapReduce view of the world, how do sketches fit in? Well, instead of generating the exact summaries, each of the mapper nodes is now going to make a sketch, here represented by the little pink scrolls. Remember, sketches are small. That's why we're interested in this. That means sending them over the network is super cheap. So the shuffle step in the middle is really scalable. And then the next benefit is once you get to the reducer merges the sketches and is only really holding something that was the same size as the sketch down here in the first place. And the reducer can operate over that sketch as if it were just a single one that it had received. It has the same type of properties and the same behavior. Overall, what it means is this MapReduce view of the world is really something more akin to like a reduced MapReduce view of the world, because the mappers themselves are also squashing that data down to something manageable. Again, that was a simplification. When we actually want to scale up and we have diagrams that are much more like this, and of course we might be tiling them many, many more times with many more shuffles, we're going to see an even more dramatic benefit. Another place where we see sketches is when you want to do time-windowed data analysis. So here we can think of a window of arbitrary size. Here I've chosen 3-day computations. And the question is, How do I get my distinct count over 3 days worth of data? Now, of course, I can get my count out for day 0 and for day 1 and day 2, but I can't actually combine the counts. And if you think back to what I said on the second slide, that's because the counts themselves, or rather the unique counting problem, is something that's called non-additive. It means I have to store some sort of data structure around that summarizes that problem. Overall, if you wanted to get this type of query answer exactly, you would have to process each of the daily data sets once. So you get the bitmap into memory. And of course, processing large data repeatedly, that's expensive. Instead, we'll do something like we did in the MapReduce diagram. I'm going to process a single day's data, generate a sketch, and then ignore the data. Process the second day's data, so on and so forth, so that when my time period is finished, I can just roll all of those sketches into one through the merge operation, and I've got my complete analysis for that time period. Now, I've used days, but it doesn't have to be at the day level. We can choose any granularity we want. You can generate a sketch per hour, and then roll hours into days, days into weeks, weeks into months, and so on. What this really means is, by exploiting this mergeability property for sketches, you can do time windowed reporting really easily. And there are other cool things you can do, like late items become easy to deal with. If you do a brute force analysis, you have to wait until a certain time period closes before you can even start processing the next one, and that's a real pain in practice. So late items can go into a separate sketch and be merged in. It makes it easy to deal with time zone differences when data is coming from different areas all across the world. Overall, what we're really seeing is that sketching allows you to simplify your architecture. So imagine you have this type of view where we have many rows that represent different dimensions that you're interested in. We can now, because the sketch is so small, on the order of kilobytes, store that sketch in a hypercube and treat it as another column in the hypercube itself. So imagine each one of these sketches represents a daily unique count, for example. Then through the merge operation, I can union on the sketch column and get, let's just say we've got 30 rows, 1 day for every month, union on the sketch column, and I get my monthly count out easily, and it's really quick. It can be really flexible. You can design different types of user-defined aggregation functions. So this is giving you a lot of flexibility by embracing approximation that brute force analysis would not allow you to. Overall, what I expect you to see if you adopt sketches is lower system cost. And the reason is because we can keep these small things and send only these small sketch objects. It's going to simplify your architecture, but it's crucially going to allow you to get near real-time results. Again, when we think about time reporting, or time windowed reporting, there is going to be a lag on how fresh the results are. This is because you always have to wait for a time window to close before you can go on and do anything else. With a sketch, we'll just read it in, and then we'll ignore the data and just keep the sketches that we're interested in. Because these are so small, you get a real speed win as well. So we have sketches that can do like continual or near-time reporting in 15 seconds, whereas before you have a daily to weekly lag. So that's a huge win. But it's not just unique counting where you see sketches really add value. A lot of companies are interested in counting unique identifiers with set expressions or doing filtering over their user data sets. We have different types of sketches, but they do exactly that. If you want to understand quantiles or histograms or distributions over particular columns, we have sketches for that. Again, the key point with all of these problems is not that the problem itself is difficult. It's that it's non-additive, and therefore it's difficult to scale in a very, very large system. You might look at this down here, uniform and reservoir and weighted sampling. Yes, it might be simple, but doing that so you have consistent samples over various time periods that you can have confidence in is difficult. You very well might be familiar with the heavy hitters or top K problem in the database world. There is a sketch for that. So just to give you a bit of a carrot and to prove that I'm not pulling the wool over your eyes, here is just a small example. It's a very small example. So I have an open data set. It's a snapshot of the Bitcoin transaction graph from the years 2011 to 2018. You can all go and get this data set from the UCI ML repo. It has a bunch of columns, but the two that we're interested in are address and year. Now, address is just like a user identifier, and the year is, of course, which year the transaction occurred. And again, we'll just take our most basic query. How many users performed a transaction between 2011 and 2018? Except, I'm going to add a twist. I'm going to make sure the data is partitioned from 2011 to 2018, and that's to simulate 8 yearly independent data streams. And this analysis is really straightforward. You can go and pip install Datasketches. We've got it on PyPy for you to use. And then in step 2, this is just me defining one sketch per year. And this is our default. It's called a hyperlog log sketch. This is, I would say, the entry-level distinct counting sketch algorithm. And then in step 3, I'm going to iterate over the years. Of course, in practice, this will be done in parallel. You wouldn't do this in a real system. Iterate over the years, and then for every year, just update that sketch. And you see in this step down here, all I'm doing is sketch.update user ID. And that's because sketches, a lot of the time, are built upon something called a hash function. And the hash function deduplicates the input. So we don't even need to worry about sampling users or anything like that. Through deduplication, it's all taken care of. Now let's have a quick look at the results. So in this table down here, we see that the true counts for every one of the years is about 360,000 user IDs having a transaction in that year. And even with these default settings, we tend to see that the hyperlog log sketch is giving us pretty accurate estimates. In fact, they're all within about 2%. Now, in practice, of course, you won't actually be able to evaluate the percentage error, but we do have, and we've gone at a lot of pains to provide error bounds for the users so that you, when you use these algorithms, can have confidence in the outputs. They are, after all, approximation algorithms. But now we get to the interesting bit. So all of these sketches, as I mentioned, were small. Although the data set I was showing you was not itself large, even at the yearly snapshots, we're talking like on the order of tens of megabytes just for that data set. Then when I've read it in and generated the sketch, you can serialize it. As shown in this table, each of the sketches is about 2 kilobytes in size, so they're small. Now when it comes to getting the overall count, I do a very similar thing. I instantiate what we call a union object, and now I can just iterate over my years, or my yearly sketches rather, and populate those into the union object. The union object works very much the same way as an individual sketch, so this is nice because I can just iterate over years, which is significantly easier than iterating over or pre-processing the data set all over again. Now when we get down to the final bit, the really interesting thing here, the union size. The union, again, same size as the sketch, kilobytes, very small. And as you see, the estimate, the center of that second table, very close to what the overall count is. Again, going back to what else you might want to do with this data set, if you want to do set operations and really understand and interrogate the types of users you have and understand what that set behavior is like, then you can use something called a theta or a tuple sketch. If you were interested in another common query, which addresses perform the most transactions? Again, at the yearly level or over the full time frame, you'd be interested in something called a frequent item sketch. If you're interested in what's the distribution of users, how many addresses occur in a certain percentage of the stream, that's a quantile sketch, and we have various different algorithms for that. They each have different trade-offs depending on what exactly you need. And if you wanted to, say, really understand particular users and go and query different addresses, then you could, to get their frequency, then you could use the count min sketch. But the key point that I really want you to take away, please, is that all of these sketches are mergeable. That means it's going to simplify how you can build an architecture using the sketching algorithms. So some other key features that I'd like you to take away. Unsurprisingly, given the example I just gave you, we have Python bindings. Now, I'm sure we all know if you're doing big data analysis, you probably don't want to do it in Python. And of course, the Python itself is built upon C++, very performant C++ code. We also have a Java library with pretty much entirely the same set of algorithms in as well. And the really nice thing is that these algorithms, we've made sure that they are cross-language compatible. So depending on what stack you have or what you're doing, you can build sketches in Java somewhere, save them, and then load them on another database elsewhere or in C++ and carry on thereafter. You'll get the same outcomes. We have extensions to a bunch of different database models, Druid, Vertica, Hive. There are people working on Pinot. There's a bunch, and of course we'd like to expand that as well. We do have a very active community of scientists and engineers. Certainly the people who have kicked this project off, it's very close to their heart, and they would really like to widen that community. But another really nice thing about our library is that we have a bunch of these characterization tests, and they're all open source as well. Now, if you go online and you go and check other vendors' sketching algorithms, you won't find graphs like this. And these graphs are really important because they will inform you as a user exactly how the sketches are working. You tend to get random outputs because they are approximation algorithms, but you need to, as a user, understand the distribution of the outputs that you're getting. And we make all of that online, open online. So finally, I would really like you to ask of yourselves, how much is your business willing to pay for an exact answer? Sure, you can brute force a bunch of your queries, palm them off to the cloud, it's fine. But it's going to cost you. And if you build all of the infrastructure, spend all the time and the money to build that infrastructure, to get exact solutions, there's going to be two more problems. Exact metrics are almost never exact in practice, number one. And number two, it's going to be really difficult for you to go back and debug and understand where you're introducing problems and how you can simplify your life. So I would ask that if you want to reduce your resource usage, please consider using Apache Datasketches. We're open source. We're very, very open and willing to hear from people. And we want to encourage more people to, I would say, benefit from the huge gains that Sketches will enable you. Thank you very much for listening. I'm happy to hang around for any questions that you might have. I think there is a microphone coming around if people have questions. There's one here.
Sorry. Come in.
Just there.
Hi there. Thanks for this. There was also another Apache project called Apache Aero, where you had in-memory calculations of large matrices, a large data set. How's that resembles to Aero?
Sorry, Apache?
Aero.
Okay, I'm not familiar with that. I don't know if the mic has got. I'm not familiar with that open source project. So there are a bunch of sketches that have been designed for large-scale matrix and vector operations. We have developed a few of them, but haven't had the uptake that we would like, but it's very much something that we would love to get into in future. Something like frequent directions algorithm, which is like an approximate singular value decomposition. Again, really benefiting from this mergeable property. So we are not related or don't have contact with that project, but if it's something you're interested in, you know, we can choose where we invest our time.
Hi there, that's really interesting technology. It looked like you were doing sketches of about 2 kilobytes,
Yeah.
getting you about a 2% error.
Yeah.
So 3 significant figures is about a 1 per milli error, about 0.1%.
Right.
How does that 2 kilobyte scale to get down to that kind of error rate?
Yeah, so the error, depending on which sketch you're interested in, the guarantees typically go like 1 over epsilon, or at least from the academic papers, the guarantees typically go with 1 over epsilon squared, which is like a 1 over square root of k in your number of buckets. But some of them, there are different sketches we have, like the frequent item sketch, I think behaves more like a 1 over epsilon. So you will do, the performance is not the same, but for all of the sketches in the library is the point, yeah. And there is definitely this trade-off between size of the sketch and accuracy that you're interested in, yeah. A lot of it is very much characterized on our website. Oh, we've got one more just down here, yeah.
Hi there. Do any of the sketches support other sort of set operations other than union? Do you have like?
Yes,
Okay.
yes. So if you want to do, in fact, I think you can do arbitrary set operations on the theta sketch. Yeah. If you're interested in that, we can talk afterwards, yeah. Great.
All good? Thank you very much.
Thank you.